All right, so in this video, we're going to prove that the derivative of e to the x is equal to e to the x. And we're going to prove this under the assumption that e is equal to the limit as k approaches 0 of 1 plus k to the power of 1 over k. So then how do we actually start this proof? Well, we could start out with the definition of a derivative. So this is the definition of a derivative expressed as a limit. And so we're just going to replace our function with e to the x. And so this is the limit that we have to evaluate. We essentially have to prove that this limit is equal to e to the x. So where do we even start? Well, we sort of just have to play around with it. Notice that e to the power of x plus h contains a sum of two exponents. Well, there's this property of exponents that states that this is true. And so we're going to apply this property of exponents to the e to the power of x plus h. And so this is what we get. Now notice that the two terms in the numerator both contain e to the x, so we can factor out the e to the x. So this is what we get. Now this next step may seem a little weird, but what we're going to do is we are going to pull the e to the x outside of the limit. But why are we allowed to do that? The reason why is because as h approaches 0, nothing's happening to x. The reason why is because in the definition of a derivative, when we take the limit as h approaches 0, it's just h approaching 0. Nothing's happening to x. And so because of that, we can pull the e to the x outside of the limit. So now, this is the limit that we have to evaluate. Now this next step may also seem a little weird, but what we're going to do is we are going to take the numerator and we are going to set it equal to a new quantity, m. So we're saying that m is equal to e to the power of h minus 1. So what we're going to do is we're going to take this equation and solve for h. We'll first start by adding 1 to both sides. You get m plus 1 equals e to the h. Well, by definition of the natural log, this means that h must equal natural log of m plus 1. So this is m in terms of h. This is h in terms of m. Now notice that as h approaches 0, m will approach 0. And just to be clear, the reason why is because as h approaches 0, you get e to the power of 0 minus 1, which is really just 1 minus 1, which is 0. Therefore, m approaches 0. So what we're going to do is we are going to rewrite this limit in terms of m. We're going to replace e to the h minus 1 with m, and we're going to replace h with the natural log of m plus 1. And remember, we're taking this limit as h approaches 0. As h approaches 0, m approaches 0. So we're going to be taking this limit as m approaches 0. So now we have converted our limit completely in terms of m. So this is the limit that we're going to evaluate. Now, first of all, notice that m plus 1 is the same thing as 1 plus m. And having an m in the numerator is the same thing as if we had a 1 over m in the denominator. So we can all agree that this is true. So really, what we're going to do now is we're going to take the 1 over m and we're going to move it inside of the logarithm as an exponent. If you recall, that's the logarithm power rule, which states that this is true. And so we're going to apply this property to the denominator. So as you can see, we have moved the 1 over m to the inside of the logarithm as an exponent. Now notice, we're taking the limit of a quotient. There's this property of limits that says that the limit of a quotient is equal to the limit of the numerator divided by the limit of the denominator. So we've applied that property of limits. Now notice that the limit of the numerator is just going to equal 1. But the limit of the denominator is a little bit more complicated. But it turns out for the denominator, we can apply another property of limits. And this property of limits states that this is true. And so really, it's a property of limits involving composite functions. What's basically going on here is that you can take the limit and move it inside of the function f. We can think of the natural log as our function f, right? We're going to take our limit and move it inside of the natural logarithm. So this is what we have now. But this limit is e, because as you can see, this limit is the same exact thing as this limit, just instead we're calling this k, we're calling this m. So we know for a fact that this limit is e. But the natural log of e is just 1. So you have e to the x times 1, which is just e to the x. And so this would be the derivative of e to the x. And that's how we could prove it. And so, yeah, this is pretty much it for this video.